The picture the textbook shows the relationship between pods and resources. Let's check what each element does. The pod in the center is the minimal unit for running containers and is where one or more containers run directly. The deployment in the upper right can be thought of as the application that encapsulates the pod. The deployment manages the replica set and acts as a controller for the replica set to maintain the number of pods. Below it, the stateful set manages a group of pods based on the same container specification as the deployment. Below that we have job, cron job, and daemon set as resources that can control the pods. Job is used to control batch jobs, cron job is used for time-based tasks, and daemon set runs a pod on each node in the cluster and ensures that only one pod exists. It is used to run certain system-level applications, such as log collection and resource monitoring, that run on the same node and manage only a specific few pods. Services on top of pods is used for accessing pods. They forward access traffic to the pod with a static IP address and perform load balancing. The ingress service to the left of services load balances network traffic coming into the server. It forwards requests based on layer 7 HTTP and HTTPS protocols and distributes traffic by URL based on domain name and path to make the service accessible. Config maps store configuration information in key value pairs that your application needs. Config maps make it easy to isolate configurations and use different config maps in different environments. Secrets allow you to store and manage sensitive information, such as passwords, credentials, certificates, and private keys. Finally, PVCs, located at the bottom of pods, are resources that allow you to request persistent storage. You use PVCs to specify the type and capacity of storage, and the best matching PV is assigned to your PVC request, making the external volume available. To make it a little easier to understand the resources we've been looking at, I've put together an illustration. Within a deployment, there are multiple replica sets, and within each replica set, there are pods. And within each pod, there are multiple containers. So we can deploy from a big unit called a deployment to a small unit called a container. Of course, you can also deploy just the resources separately. Next, let's talk about pods, which are the smallest unit in which containers run in Kubernetes. The word pod is similar to the word pod for a bin pod, and just as a bin pod can contain multiple beans, a pod can contain multiple containers. Containers are created and run inside of pods, and Kubernetes doesn't manage single containers, but rather bundles them into units called pods. Next, we'll look at services, which are responsible for making internal pods accessible from outside the cluster. Pods themselves have their own unique IPs, but since pods can be created or deleted, their IPs can change. Also, you can't directly access a pod from the outside. This is where the role of a service comes in, which uses a static IP to lock in an IP and make it accessible from the outside. The role of a service is to provide a fixed IP and support load balancing between pods. A service can support one or multiple ports. Next is the characteristics of ingress. Ingress is responsible for load balancing network traffic coming into the server from outside the server and performs L7 load balancing functions. It provides external URLs to services and distributes traffic to different services based on the URLs that access the cluster. It handles TLS and SSL certificates and is responsible for specifying domain-based virtual hosting. The following are the characteristics of a replica set. Replica set maintains and manages the number of pods and keeps the number of running pods stable. If you specify that the number of pods is 3, it ensures that you always have 3 pods. And it has a feature that guarantees availability for any number of pods. For example, if one pod is suddenly deleted for some reason, it will automatically create a new one to keep the number of pods at 3 again. Moving on to the characteristics of a deployment. A deployment is the primary controller in Kubernetes and manages replica sets to provide more granular control over the deployment of your app. It maintains the number of pods and rolling updates occur on deployment. Next, the characteristics of a stateful set. A stateful set is a workload API object that you use to manage stateful in your application. It manages the deployment and scaling of a set of pods, ensuring the order and uniqueness of the pods. It also manages pods based on the same container specification, maintaining the uniqueness of each pod. Although these pods are created from the same spec, they are not interchangeable. This means that each pod has an identifier that persists across rescheduling. If you want to use storage volumes to provide persistence for your workloads, you can use stateful sets as part of your solution. Let's compare the deployment and stateful set we've seen so far. A deployment handles the creation, replication, and deletion of a pod as a set, from the perspective of a supervisor managing the pod. Depending on what's set in the replica set, the pod can grow and shrink abruptly, and it doesn't save the state of the pod in the process. The temporary storage that the pod is using internally is only valid for as long as the pod is running. And when it's deleted with it. If you're a deployment and want to store some of your pod's state, you can mount and use external storage. By comparison, a stateful set manages pods in a stateful way. It gives each pod an identifier upon initial creation, so that if the pod is recreated, it will retain its state. Pods have unique names, and are in the same order inside stateful, even if they are recreated. This is typically used when you want to lock in a pod's DNS, or when you want to set up storage to stay the same. In a stateful set, pods are individually allocated and use storage, called PVCs. Next, we'll talk about jobs, which are responsible for specifying multiple pods to catch and setting them up for successful execution. Jobs are characterized by their use in batch jobs, ad hoc jobs, and other jobs that run once and end. It guarantees the successful completion of the caught pods and can be categorized into single job, multiple jobs, parallel jobs. Cron job works as a scheduler to execute job. It's used when you need to run a job repeatedly at a set time, such as backing up data or sending emails, and can be thought of as similar to cron tab in Linux. A daemon set is used to run specific pods across a cluster, or to manage specific pods that need to run on a specific node, or on all nodes, at all times. It ensures that one pod runs on every node, and is used to manage specific pods that need to run on every node at all times, such as log collectors and monitoring agents. Persistent volumes. PV refers to the volume itself. It is responsible for connecting to storage outside the cluster, is managed independently of pods, and has a life cycle. A persistent volume, PV, is storage in the cluster that has been provisioned by an administrator, or dynamically provisioned using a storage class. When a user makes a request through a PV is allocated to match the request. The relationship between PVs and PVCs is bound in a one-to-one relationship, and provisioning is created in two ways, statically and dynamically. PVC mentioned earlier stand for persistent volume claims. Instead of you requesting storage from a PV, you request it through a PVC. When you make a request, you specify the storage capacity, access method, seller, etc. to the PVC, which then makes the request to pivot and connects the PV to your pod. SC stands for storage class, and is a resource that organizes storage using a number of different things acquired by PVs. Predefining storage classes allows you to create PVs for them on the fly and is used when dynamically provisioning PVs. Therefore, you must have at least one storage class pre-created to enable dynamic provisioning. This picture represents the life cycle of PV and PVC, which we looked at earlier. Provisioning is the stage where PVs are created, and there is static provisioning and dynamic provisioning. Binding is where you define the access and storage capacity you want for a PVC, and it is bound to a matching PV. If no matching PV exists, it will wait for one to be created and connected. Using is the stage in which the PVC set in the pod continues to be used while the pod is maintained. This refers to the step where the pod mounts the volume provided by PVC and continues to use it. Reclamation refers to the process whereby the PVC in use is initialized and recovered when the used PVC is terminated and deleted. Next is the volume structure. First, the static provisioning structure. In static provisioning, an administrator creates a number of persistent volumes, which include information about the storage that is available to each user in the cluster. In other words, the PVC requests provisions and uses the most appropriate disk prepared by the PV. This static provisioning has the disadvantage of requiring the cluster administrator to prepare storage in advance and provide it to multiple PVs, and it also wastes resources by providing unused storage. In dynamic provisioning, on the other hand, has the same role and behavior as static provisioning described above. But the big difference is that instead of pre-creating storage, dynamic provisioning automatically delivers storage on demand. Dynamic provisioning can be used in environments where storage can be provided in a fluid manner, such as public cloud environments. Also, unlike static provisioning, dynamic provisioning requires one or more storage class objects to be created in advance. The role of the storage class is to create storage volumes, which is made possible by having a field called provisioner that determines which volume plugin is used for PV provisioning. Next, Kubernetes utilizes resources called config map and secret to pass configuration information about a container. First, let's understand config map. A config map is intended to provide the configuration information needed by a container in isolation from the container, and acts as a repository for storing configuration information in a sort of key-value format. It can have anything from simple characters to large configuration files as values. And the same pod can use multiple config maps. Like config maps, secrets are a store for configuration information in the form of key values. However, secrets store information that needs to be kept secure, such as credentials in private encryption keys, and are generated in base 60 for encoding. The maximum size of an individual secret stored in memory is 1 megabyte. Every pod has a secret volume that is automatically associated with it. As you can see in the textbook, when creating a pod, if you input the config map and secret information you want to use, and the config map and secret source created in advance will be mapped to the pod. The pod's environment variables will then contain the data from the config map and decoded secret, respectively, allowing us to use the externally defined environment information. This gives you an understanding of the different resources in Kubernetes. Next, we'll explain how to manage resources in Kubernetes. Part 4. Kubernetes Resource Management. Kubernetes resources are managed using the kubectl command line tool, with configuration files written in YAML or JSON. The image at the bottom of the textbook is an example of each management tool. As followed, we'll explain how to write a YAML file using a representative example of a deployment. An example of a deployment YAML file in a Kubernetes resource. The first thing we need to do is create an API version. The API version needs to specify which version of the Kubernetes API to use to create a specific resource. In most cases, you'll write it as apps v1. Second is the kind. The kind specifies the type of resource to create. Our resource here is a deployment, so you'll see it written as a deployment in the textbook. Next is the metadata. This is where you put information about the metadata, which gives your resource a name, and is the only data that distinguishes it. Metadata is divided into names and labels. Names specify the name of the resource, while labels are organized over key values and are used to list or search for only specific Kubernetes resources. App under labels is an example of a label setup. Notice that we have set the value board-MSA on the key value called app. The fourth thing to write is a spec. This is where you define the specifics of the resource you want to create. Replicas sets the number of pods you want to burn. This is related to the replica set we talked about earlier. The selectors in the spec define which pods should be controlled and watched. Below that, match labels maps to the same settings as metadata labels, measuring the current state by counting containers and pods with the same label. continued with the specs template. The spec template sets up information about which pods to run. There's also metadata in there, which we'll map to the same settings as the labels. In the metadata, we set up at the top to make sure we run pods with the same labels. Next is the spec at the bottom of the spec template. This is where you write the settings for the container you want to run. Inside the container, you'll again need to write down the settings for the name, image, port number, etc. Among these, the name refers to the container name. The image in container specifies the image to be deployed to the container. Image pull policy is the image download policy. You can specify a specific policy, or write always to download regardless of whether there is an image. And port specifies the container port number. The image pull secret in the spec is the credentials to access the image store. For now, it only contains a name value. The last node selector is to specify a specific node to deploy the pod to. Next, let's look at an example of writing a service YAML file to manage a service resource. It's the same as the deployment resource we saw earlier, right down to the API version and metadata. The most important part of the service is to set up the ports that make the pod accessible from the outside, so this is where the ports in the spec go. Node ports set the externally accessible port number, and port sets the internal port. In protocol, we set the protocol method, and in target port, we set the container port information that we want to access. Underneath that, in selector, we define which part should be controlled and watched. We've covered this before, so we'll skip it. Finally, the type of spec used by the service. This sets how you want to be exposed to the outside, and the node port is how you can access it from the outside, through the port number. In the example we gave earlier about YAML files, you can write multiple YAML files that are related to each other as a single file, separated by 3 hyphens in the middle. As you saw in the textbook, YAML files have a basic syntax. They support to and for spaces for indentation. There must be a blank space between the key and the value. There are other syntaxes that must be followed, and these are explained in more detail on the web, which I encourage you to look up. This concludes Section 2, Understanding Containers, Podman, and Kubernetes. In Section 3, we'll discuss the open source software that manages the container platform. Good job, everyone.